go to download files and choose legacy PDB format. And now load that PDB. Have you open that with Chimera and play around with Chimera, rotate it, show it again, show the first thing, show the second, we are uploading some files. That's on. So when we open that with Chimera,
I uploaded all the files that necessary for the session in Google Drive.
you will need to download these files as well. Make a folder for it, like I do MT, for example. And place all the files, including the PDB file, and the files that you will download from the drive file into that folder. Yeah. Well, let's talk to you. Olmak değiştirici olmasın. So, have you created a folder? Yes? Is there anyone who doesn't know how to create a folder in Linux? You right-click on your desktop, for example. So you right-click and then you say new folder to create a new folder. Okay, mine is in Turkish. Yours can be in English or in any other language. It's the first option. And you name it. So this is the protein with the ligands. Then you open that with Chimera. And you can translate it, rotate it, play around with it. There are many various options in Chimera. Have you opened that? Yes. Wait until everyone is. So you see this fish protein is in complex with phenol compounds and other ligands, and there are water molecules as well. So I want to go to select now. You can select the chain, you can select the chemistry, you can select the residues, right? You can select all non-standard residues, or you can do it one by one, like heme, water, and I think the phenol. So I selected all non-standard residues because I want to separate my protein from all non-standard residues. This is a crystal structure, right? And I want to separate my ligand, which is the phenol and the protein. And then we'll start to do the simulations, but there's a problem. The ligand topology and parameter files have to be prepared by me. All right? For phenol. Okay? So I will show you step by step how to do that, so that you can learn how to simulate a protein and ligand. After you select it, you go to actions, and then atoms and bonds, and then to delete. So all of them are gone. I have my protein on. You see? Okay, then you go to select all non-standard residues by clicking the pen. Then what? Can you show me? Or you can delete them one by one if you want. So afterwards, you save that file as a PDB. There is save PDB, and you give the name REC for receptor. And then save your file. In the same folder.
No, I mean, you should install the camera.
Yes.
But yes.
Yeah.
So how does you do that?
Camera. Sure, please. and then save it as a PDB file. Now you have only your protein PDB file without the link. The older one.
And here this one. And
Now, another thing that you will notice is I'm waiting until everybody is at the same stage.
how long for? Is it downloaded?
Yeah.
Now you can go to
No, it's-
the project. Did you download the PDF
No, I downloaded the folder.
and the PDF file from 14 days ago?
No, I didn't.
For JMW. So let me show you what you will get at the end.
The drives.
I downloaded this.
You will have to. But you can.
Okay.
You have to.
Okay, well.
Scan.
Download, okay.
Yeah.
Are you done with it? Did you open it?
Still download.
So from the downloaded files, there is a file called GrowMax Code. I want you to open it with gedit. This file explains everything. Bana bak. Size rahatsız etmeniz ya. İsterseniz bırakın. Are you done?
Yeah.
So it will be this is a very short simulation, but it will be a simulation like this one. The trajectories that are moving. And you can run it for longer time on your computer or server. So are you done? Did you save the PDB file as receptor, REC? I want to control the first time here on some this is the topology that I'm
Yes.
You know what?
Same question. Hocam şeyleri internetten veriyor. Base'leri var. Onun içinde terminalın şeyi yok. Çalışıyor. O koddan yapmaları lazım ama
So today, which one is 5
kind of one of the global this one's about to
So I want to show you something now. When I select instead of the ligands, the protein.
have
So I do chain, and I select chain A, and I delete the protein.
Just different.
Um,
can I
So when I open it, I go to select. And let's say I choose the protein, and then I go to actions, add and forms, and say delete. So these are the ligands that are left there. Do you see a problem here in this experiment? When you look at the links. It's an experiment, X-ray study. And I see enormous issues with these ligands there. So when you look at here, there are two phenol groups that are overlapping. Do you see that? So the experiment you have to find the name. So Yes.
And you have to click on them.
so you cannot start your simulation. So the question I need to ask is, can you start your simulation with this configuration? It's overlapping, right? Yeah. That would not be nice for the simulation. So what I did is, I did a quantum mechanical calculation of phenol, and then did the docking. And one of the files that we download is called lake.mol from the drive. So when you go to LeakMol 2 that you downloaded from the drive and open it with Chimera, here is LeakMol 2. Let's open like the Chimera. Here's it.
Oh, never took it. For this.
Yeah.
Okay. Residue.
Or you can try to open it with PMD. I will show that to you.
And you have them all, just the. What?
Okay.
Not the.
So, take some pipe.
You go to file, new molecule, browse,
Thanks.
and I'm in the right folder. So here is the phenol that I calculated with the quantum mechanical calculations that you are familiar with by now. And I did the docking and isolated it from my protein. And this is the phenol, so you can open it. I want you to learn also VMD. You can open it with VMD.
You have to just type the end.
In your terminal, just type VMD when you downloaded it or installed it.
But you have to.
Okay, no problem.
So we separated the protein and the ligand one. Right, that's what we did. We had a complex with some mistakes in the experimental prime, which had to be correct. So what we did is we isolated proteins, the geometry optimization, quantum mechanics, right? And I did the docking and isolated them, and here is the ligand. So now I want you to go to Chimera again. You can close this VM. Let's close everything.
So just to have. You have your.
Everything has to be in the same folder, don't forget that. So I want you to go to your protein again, which you prepared by downloading the file and deleting all non-standard residues. And you had your protein active. Right? So we have to go to tools now, and in Chimera it's called surface binding analysis. Okay. There is an option called doc prep, as you can see. When you open that, the first thing that it says, if there are incomplete side chains, replace them using Dunbreck 2010 Ultimer library. So uncheck that. Right wall 2, we don't need that either. And then you say, okay. And then it says also consider hydrogen atoms, unspecified, determined by the name. Let's say, okay. Now it wants to add charges. For other residues, we will use gas tiger, and we will click OK. I will explain everything in our lecture. And now we can go to save file and save PDB. Okay. You can rewrite it and rename it again REC. And it will replace the file that you had in your folder. Let's replace it. So we have the ligands, we have the protein. And we split the complex into ligand and receptor. The ligand has the MOL2 format, the receptor has the PDB format. Now, I want you, because we have to do some changes, I want you to open the ligmol2 file using gedit, okay, Gedit. So when I open my terminal, I will use not BI. BI is too complex. I will use gedit because you are not familiar with editors. So I will write now gedit. I will make it larger so that you can see it easier. And then ligmol2. And now it will open the ligmol2 file. Okay. So now you see the changes that you need to make. Below the first line, which is with add tripos molecule, which has to stay there. Don't play around with it. What is written in the second line? Do you have a phenol there or something else? What do you have here?
I just reported this money.
What are you doing? Yes, you opened the complex in there. Phenol has to be written there. Or lig can be written there. Are you done? So next step is the Perl script that we had that starts with sort mol 2 bonds, right? That's the title of the script. And we say lig mol 2, lig mol 2. So this is to fix the bond order in your ligand. I had it fixed for you, but I want it for this week. Did you do that? Yes, okay. Now go to the browser. I have my Firefox and Go to Swiss parameters. Swiss param. Oops, sorry. Swiss param. CH. So what is the Swiss param? Swiss param. Go to the old version, not the new version. So it provides the topology and parameters for small organic molecules like the phenol molecule with the charm, all atom force field parameters for use with charm and Bromex. Charm is another software that is used for molecular dynamic simulations, and Bromex is the one that you're using. So in Swiss parameters, you can obtain the topology and parameter file, upload your lit mol2 file now. So when you upload your lit mol2 file, it will start generating the topology and parameter file. Refresh the page and download the lit zip file afterwards and copy it to your own folder wherever you have the Bromex file. So you can get the topology or parameter file of your organic molecule. It can be a toxic molecule, fish, for example, and you want to study its interactions with a protein or some other viable fish, and how it affects the biomolecule, etc., or you want to do drug design, or you want to do some other things. Swiss Parent is a nice page for obtaining the topology and parameter files for organic. Then you want to use charm or gold.
So should we download this?
What? Do you have Linux?
Oh, I just.
Why didn't you install Linux? It was in the past, so you cannot do the simulation. No. So I would sit next to someone who has Linux. so that you can run formats. If you want to watch it, like how they do that. For example, this group here, they did everything. You can sit close to them and watch how they are doing that. Do you have it? Is it fun? Do you have the good part? Yeah. It's after the questions. Will you download it? Okay, good. So after you downloaded it, you want to extract the files. So when you press like to zip, which should be in the same folder as your other files for R&D simulation, choose replace nothing, because you don't want to replace the like Mol2 file. Okay. Did you download all the MDP files from the drive? Yes. Okay. Lisa, Giant, have you downloaded everything? All right. So now we can start using the file that I sent you that was on Drive. It's called Romex codes. Yeah. I explained everything that I'm explaining here, written here, what needs to be done step by step. When you open Romex codes with gedit, you will see that we have prepared the ligand and receptor in Chimera. And we opened the LICMOL2 file, and in the second line, we checked if it was written LICMOL2. And then we did the bond orders with the Perl script, sort MOL2 bonds per. We did the Swiss parent topology and parameter generation. We downloaded the zip folder from there on. And we copied all MVP files into this working folder. And now we can start with the comments. The first comment, do you have the file open? The first comment that you want to type in your terminal is GMX PDB to GMX minus F rec.pdb minus IGNH. This will ask you which parameters, force field parameters, you are going to choose for your system. Because the Swiss parameters creates the topology and parameter files which are compatible with chart. In TIP for order. So 8 and 1. Did you choose it? Do you have it? Was it 8?
Yes.
Yes, 8 was charm and 1 was TTP, right? TTP is the order model. Charm is for the protein. And for the receptor, which was our protein, we did the force field parameter selection. Now for the ligand, we need to do something here. Type in GMX edit conf minus F lig PDB minus O. Minus F is for file name. And minus O is for output file name. Input file name, output file name. So lig.go, it's written in the GROMACS codes. It's the next step. So what does it say in the GROMACS codes? It says afterwards we are going to open the gedit, conf.grow, and lig.grow topology files. So copy content from third line, from the third line of lig.grow to conf.grow file up to the second last line, where the protein ends. You copy and paste the ligand file so that we can merge files. So if you want me to show that to you, it's looking like this. Let me open that with GPIT. Huh? Ah, Python. So it says cytochrome C peroxidase. And then you have your amino acids here, and I'm scrolling down, and it's the protein. Okay. It's the protein, it's the protein. You see the coordinates. And then after the protein ends with the last atom, I copied and pasted my ligand into here. So I want you to do the same thing. The conf.grow is about the protein and the lig.grow is about the ligand. From the third line up to the second last line, you need to copy and paste it after scrolling down in your conf.grow file to the end. The second last line, right-click, paste the information that lig.grow had in it. Do you have to see?
Yes, after you do some, you have.
Can I see? Yes. Now, I want you to check. Very good. Have you done it? Where are you? Oh. Do you have one? Okay. So the last line here is 4556. Can you see that? I want you to go to the top and type here 4556 minus 3. Why do I subtract 3? Because the first line has nothing to do with my protein ligand. It's in the definition title. It doesn't have the data that is required in it. The second line is just a line number, and the last line has nothing to do with it either. So minus 3 lines. And type in there 4553. It's equal to 4556 minus 3. So you are subtracting 3 lines from the total number of lines. Anyone else do that too? How is it going over there? So, and hold going over there. It's a difficult one, right? I chose the most difficult. So now let's check with Chimera and open Grow after you did that. So save that file, right? Don't forget to save that file. And now with Chimera, you can open Grow. So here. Let's see. Yes, it opened and it looks like I have my ligand and my protein. Did you open yours too? Good. Sorusu olan var mı? Sorusu olan yoksa, when you don't have any questions, I suggest you to read the code that I will provide. Everything is explained there step by step. What you need to do to perform a simulation in a protein and the ligand, including Swiss form, everything is presented. So try to do that at home, and you cannot do it here because of some technological issues like computers or so. So, okay, we can close it now. Now the file opens properly as we have seen. We can close it now. Now we want to edit the topology top. Look at the file. Look at the Gromex codes file again. So it says we need to edit the following in topology top file. First, we have to open the topology top file with gedit, for example. Or you can use another editor like VI or Nano, but they are more difficult. So gedit is very easy to use. So after you open topol top, you add below where include force field parameters, include Ember GSFF force field ITP is written, or charm is written in this case. Semicolon, include ligand topology, and then include lig IT. So when I open the file, it looks like this. So under below include force field parameters, and number include charm 36 July 2022 to FF force field ITP. I use charm 36 parameters. I'm not sure which one you use. You write include ligand topology, include lig ITP. Manual. So it's this line that you need to include, 23 and 24, lines 23 and 24, this part. Okay? Yeah, this part. Do you have it? You have it too? Yeah? You have it? Okay, now at the end of the file, you will see something that says protein. Go scroll down to the end of the file, and you will see something like protein chain A, number moles 1. MOLS 1. Under that, write that below that, lig 1. Don't write lig fix like I did, write lig 1. How many lick files do you have? How many licking files do you have in your file?
So,
Very good. Very good. So you're learning how to do molecular dynamic simulations. That's great. And this is not an easy case. Because once you learn that, you can do also drug interactions with proteins or DNA or RNA and carbohydrates and lipids membranes. You can do whatever you want. So, did you add one, like one, under the protein near end of the file? Top, top. You need to write lick one, not lick six, lick one. In my case, I mean that. All your files have the name lick, right? So, you need to add the name lick. That's one. So, afterwards, you need to save the file and close it. Okay. Let's go to our file again. We did that. We edited the topology file. And at the bottom of the same file, do you need to add link one line exactly below protein chain A? We did that. And then in link ITP, it says, edit the following. Open with GE, edit, link ITP. You don't need to change anything because Chimera did it automatically. Okay? But I want you to find molecule type, name, and it says link GMX2 free. The molecule type, name, link free. In certain cases, this will already be link free, so for such cases, no changes needed. And Chimera does that automatically. That's why we prepared that with Chimera. And you should have that number free in your file. You have it. Can you hold? Okay. So you have the description though in your case, so you can do that step by step. Yeah. So now we can start running GrowMag. Everything is prepared. Each file is ready. We can start with GMX edit conf minus add conf grow minus D. 1.0 is 10 angstrom. Okay. If you had 2.0, that would be 20 angstrom. And I'm using a tree clinic box minus O output file box grow. Can you type it in? Or copy and paste in your terminal. So it looks like this. You can copy this line and paste in your terminal. Oldu.
Linux'ta değişik sanmış.
So, what happens when you do that? Does it give a joke at the end? Yes. So that means you were successful in creating that. Now, next step is The second line, solvate. So we will use SPC water molecules, for example, or we chose tip treatment, but we can write SPC here. We are solvating the box. You can copy and paste this comment, GMX solvate, and use your terminal and paste it. And then we will solvate the ligand and protein. Is it there? Did it give a joke? Great. And then we will gromp our file with ions and DP that you downloaded from the drive file, which I prepared for you. So take the first one. I put both comments there to gromp it, but take the first one, it should be fine. So we are here now. GMX from ions MDP. Copy and paste it in your terminal. Let it run. And now we need to neutralize the system. So the next comment is GMX genine. Make sure that it's uniform. Otherwise, with the periodic boundary conditions, which I will explain in our practice session, we won't have infinity charge in the system. And I think that's not good. Or you don't have to use periodic boundary conditions. So, have you done that? Have you done that?
Like that's on the file being to grow to them.
Which is there? What is there? First, okay, we'll get something. Fixing the problem. Do you want my config file? And then we do energy minimization. The energy minimization comment is this one. Or you can give the other comment, but I usually use the first one. And I provided you the energy minimization MDP file. So you have all the files to conduct or to run in these simulations on your own. So and then after the energy minimization, when you are done with it, we do GMX MD run minus VDEF and MEM. You don't need to edit the NBT and NPT and NP and NP files because I already edited them so that we have floating our simulations and on and all that. So this is the most complex one you can get in. Or you can have transition meta lines for which you need to create the parameters. That would be a little bit more complex. Or a metallic surface would be complex. But this is not easy either. After that, we need to edit the NBT MDP file, but it's already edited for you. I did that, and you downloaded it. And then we need to make index files. So the command for indexing the ligand is make NDX. And you choose 0 and factorial a hydrogen star and do a quick there. And from there on, we give this comment and select group 3 from here on. And then open the topology top file. And after where it's with written, include position restraint file, if the phosphorus include phosphate ITP ended, there you copy and paste this comment. So it looks like this. Here's the topology file. So the topology profile looks like this. Okay. It's already edited. And now for the system, we need to make another index file. And that means we will use the minimized energy situation, the grow file, to make the index file. And we will choose 1 and 13 and then do quit. It will show you on the screen what 1 and 13 are while we are selected. And then you don't have to edit the NBT or NPT NDP files. I did that already for you. You type in this comment, GMX Gromp NBT NBP for the energy minimized system. And this is our short NBT run. What is an NBT? This is a canonical assembly. That means the number of particles, volume, and temperature remain constant. Pressure, energy, etc. So step by step. And then we do the same thing before our actual NPT run in the NPT assemble, isobaric isothermal assemble, using the last NBT system. you can type in this comment. And from there on, we go into the final ND run. And we give in this comment, GMX ground minus at MVP, which I prepared for you. You downloaded it. And afterwards, you will run your simulation. It will take some time, especially since we are doing that on our laptops. And then you can start with the analysis. After the analysis, so after the run, when we start with the analysis, you can recenter the protein because it's moving around in the box, right? It's a 3-clinical box, and you can center your protein in order again. And this is this comment here. And rewrapping the coordinates without changing them. So you don't play around with the coordinates, but you just center the protein. Okay. So, and then for RMSD, root mean square deviation calculation, this is the comment. After you centered that. For how many nanoseconds you want to have it, you can decide that too. That's the second comment. And then you can open that with XM Grace RMSD. So it looks like this, for example. RMSD. So here is the RMSD. After you installed Grace, it's very easy. It's a very short time simulation, so it looks different than usual simulation results. But when you run it longer, you have the root mean square deviation of the simulation. Based on the root mean square deviation of the protein, you can decide if it's incorporated or not, the system. And you can use also energy criteria or pressure criteria if you do have NBT assembly, for example. And after RMSD, where am I? We can calculate also the root mean square fluctuation, which gives us an understanding of the flexibility of the protein residues during the dynamics. So, for example, you can give this comment and you can grace it, XM grace it using the output results. So here's the output file. I didn't calculate it. I didn't calculate it. But you can plot it using this comment. And you can calculate the hydrogen bonds, the average hydrogen bonds, or the hydrogen bonds per trajectory, and you can define for how many nanoseconds you want to calculate that, for example. And you can plot it again with XM Grace, or you can plot the radius of gyration after calculating that. This is the comment for calculating the radius of gyration, which is a sign of its compactness. And this is the comment that we are using. And then you can look with XM Grace to the gyrate XVG results. Let me see if I calculated that. Yes, I did. So it looks like this. And this is a very short simulation because it's on my laptop, not on the server. And so it doesn't look like a radius of gyration that I usually have out of my simulations. It's a very short time simulation. It's just few steps. So this is how we do the simulations and how we do the analysis. And you have all the files, all the input files, all the code. For putting the or DNA, RNA. I will show you the difference too, but you can simulate lipids, you can simulate carbohydrate complexes, whatever biomolecule you are interested in using Romex HR. So this was it. And one thing that I want to show you, a friend who does a great work but explains that simpler than I do, if you are a beginner, is Justin Lenko's webpage. And he has great Romex tutorials, not this difficult, okay? He's at Virginia Tech. And when you go to this page, you will see, for example, lysosome in water. This is for the first tutorial, okay? When you click on it, he explains everything one by one, how to do that. You can start the tutorial, but these are two simple simulations. So if you are interested in just a protein in water without the ligand, etc., for which we needed to get the parameters, etc., so you can start doing these tutorials actually too. Okay, so he sets up the topology next for the protein, for the system, and then solvates that. And then, like we did, he adds the ions. Okay, using these comments. And then next is energy minimization. We did everything with a ligand in the vicinity of a ligand. And then equilibration using NVT and NPT assembles. So NVT was first, equilibration phase 2 is with the NPT assemble. And then he starts with the production run like we did. And then he shows also how to analyze the systems like I showed you. So it's a great web page if you want to exercise more at home, if you want to practice more at home. Okay, this is just one tutorial. So do that at home, but try to do the ligand protein with Swiss perm. And there are other sites which I will explain, and we will talk about the theory of molecular dynamics simulations in a few minutes. But first, let's have a break. You are very tired.